Here we have a block of mass 40 kilograms, and as you can see, there are two forces acting on the block. We have an applied force of 100 newtons acting towards the right, and I have a force of kinetic friction, 70 newtons acting towards the left. As you can see, obviously the net force acting on this object would be 30 newtons towards the right, which means that it must accelerate towards the right as well. So as you can see, if you were to take a look at the work that's being done on this object, we can simply say that this applied force of 100 newtons must be doing positive work on my 40 kilogram mass. Why is it doing positive work? Well, because it's helping the motion towards the right, which means that it must be doing positive work. On the other hand, my force of kinetic friction of 70 newtons is hindering the motion of the box, which means that even though the box is moving forwards, my force of kinetic friction is preventing it from reaching a faster maximum speed. Therefore, it's doing negative work on the mass as well. So let's take a look at the work that's done by the applied force and the work that's done by the force of kinetic friction. If I were to take a look at the sum or the total work that's being done on the box, we can say that the total work being done on the box is equal to the work done by the applied force minus the work done, or let's put it this way, plus the work done by the force of kinetic friction. And since the work done by the force of kinetic friction is negative, we could see it's F applied delta D minus force of kinetic friction delta D. If I factor out my delta D, I can see that what I'm left with on the right hand side is F applied minus Fk, which is simply nothing more than your net force. I'm going to rewrite this equation just because I like to write things a little bit differently now. What we're going to say in this case is that for my total work that's being done, I'm going to rewrite that as the sum of all the work that's being done is going to be equal to the net force, and I'm going to write that as my sum of all forces times delta D, your displacement. Okay, so that's just another way of writing the exact same thing above there. Okay. Hopefully you guys don't have too many questions. Now, here's the thing. Yesterday we defined what work was, and I said to you guys that when I define work, it's nothing more than a transfer of energy, and you told me that energy is the ability to do work, and we went back and forth, back and forth. So let's take a look at the definition of work again. You said to me that work is the transfer of energy. If we take a look at the box up here, we can see that it's actually going to be moving from some initial velocity to some final velocity. So it's going to be gaining kinetic energy. What I could say then is that we are changing the kinetic energy of the object. So the total work that's being done on the object is equal to a transfer of kinetic energy. One way I could look at this is by saying that the total work that's being done is equal to a transfer of kinetic energy. Okay, so since the total work that's being done on the object is equal to net force delta D, I'm going to rewrite this as net force delta D, which is equal to my final kinetic energy minus my initial kinetic energy. Now let's assume for now that this block starts off at rest. If it started with an initial velocity equal to 0, what I could say is that, well, since my initial velocity is 0, I can eliminate this term altogether to say that my net force delta D is equal to 1/2 mv squared. Okay, now this equation over here is not one I want you to memorize. In fact, I don't want you to memorize this at all. The only thing I want you to understand is that the sum of all the work that's being done, or the total work that's being done, is equal to a change in kinetic energy, which is essentially your work-kinetic energy theorem. Okay. Now, if I go back up here for a second, I wanted to show you something really quickly. Let's take a look at this negative work being done on the mass. Now, yesterday in class, if you recall, I did mention that if something is doing negative work on a mass, it means that that particular force is hindering the motion of the box. So this 70 Newton force of kinetic friction is obviously hindering the motion of the box. Another way of me saying this is that, or another way of putting it would be to say that this force of kinetic friction is preventing the box from reaching a much higher maximum velocity. In other words, imagine we had no kinetic friction. what do you think the final velocity of this block would be? Well, the final velocity of this block would be much greater than if there were kinetic friction. So the question is, of all the work that's being done, if it's not all being converted into kinetic friction, if it's not all being converted into kinetic energy, what other form of energy is being created? Well, whenever we're talking about friction, as you know, is the force that opposes slippage. Okay, so we know that the force that's being applied to prevent this object from slipping has to go towards something. And I don't know if you guys remember this or not, but in class we mentioned that, if you were, I don't know, okay, zoom in here. We mentioned that if you were to zoom in to the surface between, to the area in contact between the box and the surface, you would notice that there are a lot of grooves between the box itself and the surface of the ground. So whenever those grooves come into contact with each other, you're creating a collision. And whenever you create this collision of particles, what ends up happening is that you generate a little bit of heat, or in this case, thermal energy. So what we can now say is that if negative work is being done on this particular mass, that work is being done to convert some of the work into thermal energy. Okay, so I hope that makes sense. Let's see if I can move on to the next slide. So here I have another example of a block, but this time, I don't know if you can see this or not, we have just a force of kinetic friction acting on the box. So in this case, the object is already moving to begin with, and what's going to happen is while it's sliding down the ice with some initial velocity, if the force of kinetic friction is acting backwards on this object, it should slow down until it eventually stops. It kind of reminds me of a curling rock, since our team is going to be curling tomorrow morning. So if you take a look, we're going to use the exact same principle that we talked about before, the whole idea that work is a transfer of energy. Now in this case, the total work that's being done is only supplied by the work done by kinetic friction. And since the work done by kinetic friction is hindering the object itself, we're going to say that it does negative work. So therefore, negative Fk delta D. Once again, if you take a look at the equation for the total work that's being done, the sum of all the work done is equal to a transfer of kinetic energy. Okay, so in this case, the total work is sigma W, and 1/2 mv2 squared minus 1/2 mv1 squared is your change in kinetic energy. So in this case, we know for a fact that this block will eventually come to a stop, which means that the final velocity is equal to 0. So if you take a look at what we're left with, I'm now left with just total work being equal to negative 1/2 mv1 squared. Okay, and it makes a lot of sense because if you, actually let me zoom in again here. Makes a lot of sense because if you take a look at the total work that's being done, you mentioned that it's equal to negative Fk delta D, which would be equal to negative 1/2 mv1 squared, and as you can see, those two negatives will now just cancel out. Okay, and the last thing I wanted you guys to take a look at is this one over here. What if the mass starts with some initial velocity and reaches some other final velocity? Then, well, if that's the case, then we just use the same equation all over again. And that's all I wanted to do for today. And if you have any questions, hopefully you guys will use Edmodo and post your questions online, and perhaps one of your peers will help answer the question. If not, I'll try to answer the question for you sometime tomorrow night. Anyways, it is now, what time is it? It's 11:45. Everybody have a good night. We will talk to you tomorrow. Bye-bye.